Hey everybody, today we will do another video, and today we will do I will complete or I will say I will try to do some playlist on power power systems, power system, which is basically part of power circuit analysis. So so what we will do, we will start off with balance systems, right? So a balanced power system is a system that you will, most of the time, a system will be balanced in the source, right? So the imbalance part, which is this not gonna be this video is not gonna be about imbalance loads, but the imbalance load or unbalanced load is going to be in the low side, not at the source, for the most part, right? And I will explain that eventually. But and the reason why, okay, I might explain it, just a brief explanation right now. The reason why on a balance load happen. So so in order to have a system, you need a source and you need a load, right? But the source almost always is balanced. Why? Because a transformer, three-phase transformer, you need to have basically the same amount of um, of turns on each coil. Well, if you have the same amount of turn in the primary side, and then on the secondary side, right? You have the three phases. Those turns, either in the primary or the secondary, they have to kind of be the same amount of turns. Now, the low side is when the problems come sometimes, right? But right now we will do just balance loads. So balance. So we will do balance. So balance systems, right? So basically, a balance system, we will look like this. So we will do something like this. So we will do, um, let's say that this is an AC, right? Of course, right? AC, and we have right here we have 110 volts, 110 volt angle 0 degrees, right? So then we have right. We have here we will have, and of course, right, and then we have 100. Let me see how much they have. Okay, they have, in this case, they have 110 degree, 140 degrees, right? 110 volt. Okay, and this is volts too. So 110 volt, 240, 240 degrees, right? So in this case, you got 110 volt at 240 degrees. Okay, so now we do another one, right? Because it's a Y connected load. It's a Y connected system, right? So now, so this is called Y to Y system, right? Y to Y, Y to Y system. Right. So right here we have 0 degrees, 240 degrees, and then we have 120 on the other side. So negative 120. So here we have negative 120 degrees. Oops, 120. All right. So right, so we have this, right? Now, let me bring that up a little bit because this is, I need a little space right there. So let me just put it right here. So it's 110, right? At negative 120 degrees. This is volts. And of course, this is also volts. Okay, so with that being said, we drag, so we do like this, right? So this goes like that. And then we drop this one down a little bit, like this. And then it goes like this. And then the other one goes like that, right? Over here we have we have an impedance. Impedance means resistance, right? So I think I already did a video before on impedance. So these are impedance that are over here, right? So now this is not the load yet. The load is going to be, of course, this is part of the load, but it's like a resistance in between the wire, right? Before you get to the load. So, and also it's another good point to understand that if this is a transformer, right? If this is the secondary transformer and I have a load right here, this right here, the system between phases, it's called phase voltage, phase current. Right here, anything that is outside the phases, outside the transformer, that is called line current and line voltages. It's a good point to understand because then, sometimes in the field we, working as an electrical engineer, sometimes we make a mistake. We say, sometimes we tend to call this as the phase to phase. We tend to call it line to line. It's not. I mean, this is line voltage is this one and line current this one. Inside, when you measure phase to phase, it's inside the transformer. You're talking about just the resistance inside or the impedance inside of the coil, right? Of the turns in those transformers. The turns in those coils in the transformer. So okay, so let's continue. So right here we have, right? And then we have, so now we have this, right? So now we have something like this, and then we have something like this, and then we drop another right here, and we got something like this, right? And then we got something like this. And it looked almost like a Y, right? This is a Y. Well, this is is almost like a Y too. You know, if I make this, almost look like a Y. Okay, so now let's call this A, and let's call this right here B, and let's call the C. Right, so A, B, this line right here, and then the C, right? And then let's put the numbers. So let's do 5 minus 2j, 5 minus 2j, and this is the impedance though. 5 minus 2j. And then every single one is the same. 5 minus 2j. I think it's J2. They put a J2. It's J, yeah, it's J2. So J2, right? And then J2, 5, and then J2, and right here. All right, so every single one will be the same, right? So those will be the same. And of course, if you're talking about balance system, this should have the same, not the same value of this, but they should be the same, all of them. Okay, so now this one is 10 plus J plus J 8, 10 plus J 8, and then this is 10 plus AJ, right? Yeah, or JA, whatever, right? So make sure that J8. So now we have all the impedance values, right? So now we will prove that the current in this system is the same. So therefore, the system will be balanced, right? So how do we do that? Well, if the current is the same, then the system will be balanced, right? So let's let's do this. So we know, right, that this point and this point, those are the two resistances in series, right? This point is the point. Also, those two impedances are in series, and this point and this point, they are also in series. So well, we can do that. How we can do this, right? So remember that I cannot, when I'm dealing with, in this case, I have a negative J in all of them. That means you remember that when I have a negative J, that means capacitor. That means I am negative 190 degrees, right? Now, so in this case, I will do the math for one of them, and then it's going to be the same for the other one. The angle might change, right? The angle might change because the angles over here are different. But we will figure out why. Also, I need to explain why this is 240 this is 240, right? So I will explain that too, because it might be confusing. So 110 angle negative 240 is volts, right? So now I will explain that. But anyway, so let's do the math over here. So let's calculate this. Let's call it let's call it IAN, right? Um, so let's say that IAN is equal to BAN divided by some CY value. Also tell us that the voltage divided by impedance is equal current, right? Okay, so, okay. My apply, you don't even have to, I mean, you can call it just IA. And this voltage, BA, whatever. But now we need to find CY right? And CY is going to be equal to this plus this, right? So it's going to be equal to 5 minus J2 plus 10 plus J8, right? So CY is going to be equal to those, right? So that's going to be 5, right? Now, 15. It's going to be 15, right? This 15, and this is going to be plus J6. Okay, plus J6. Plus J6. All right, so now having this, the book, I think, is kept consistent with a J6, whatever, right? So now I can find, right? So, but this is not the impedance yet, right? Because the impedance is going to be the magnitude of this, which is going to be CY is going to be equal to the square root of 15 squared plus 6 squared, right? And when we do that, we do 15 plus a square plus 6 squared, and then we take the magnitude of that. Okay, so it's equal to 16. CY is equal to 16.155, right? And those are, of course, ohms, right? Now, okay, so now we found that we have an impedance. Well, if this impedance, they're all the same. As you can see, every single one is the same. So therefore, we have the same impedances, right? All the numbers, I don't have to calculate all of them because all the numbers are the same, right? It's going to be the same. Which means this is a balanced system because I have the same impedances, right? Now I find IA, right? By taking, but now let me do something before here. So right here, I'm still not completed down with this. The reason why, because I have to find the angle. So I have to find the angle between those, which is going to be tangent inverse of 6/15. So tangent inverse of that. So it's going to be, so tangent inverse of that, 21.8. So it's 21.8 degrees, right? So as you can see now you can get a feeling and this is the most important thing, right? You can get a feeling that the resistance plays a role in the electrical system, right? The impedance. Why? You see they have an angle here. Just the resistance has an angle, which means that the angle somehow will affect the system, right? In this case, we have a balanced load. But in this case, it was imbalanced. If I have like, maybe, if I have more circuits in one phase, right? It's one of the three phases. It does not matter. And let me restate this. People think sometimes just because you have a three phase in the system, you can count that as a single node. No, there are three different branch circuits. They are like three different branch circuits. So if you load one of the phases more than the other, it's going to cause what is called an imbalanced load, and this is going to have an imbalanced current, right? So right now, as you can see, we have that, right? So that is going to be an angle of 21.8 degrees, right? So that is that, right? So now I have, matter of fact, I think the book have it at, when they do this stuff, I think, yeah, they have it like this. So let me just write out the book. So when they do this, they do it like that. So 21.8 degrees. Right. So now we know that we have the impedance. Now I will have to find this current, right? Current going in this system. And think about it. The current going over here, right? It will go over here, go into the load, and come back to another phase, right? And over here, the same thing. The current go over here, go into the load, come back in this phase. And they will just go back and forth, That's called alternating current. Okay, so now, that's what it's called alternating current, because you go from negative to positive and all that. But technically, ideal in an ideal system, it's easy to make a balance. In the real world, the real system, it's hard to make a balance. But as long as the current is not exceed the limit, and I think the limit is about it's not supposed, the current technically is not supposed to have 6 times more the imbalance of the voltage, right? The current, because the current, we give it a little more, I would say the current technically, it got to be a little more imbalanced than the voltage, because the current deal with all the heating element and all that, changes. When the system is on for a long time, it will, create heat, and that heat will change the resistance, and therefore, if the resistance changes, the impedance kind of changes, and impedance and resistance is the same. But what I'm trying to say is that if the heat increases, then the impedance increases. Okay, so if the heat increases, then the impedance increases, and then it will tend to have some changes in the impedance, and that's why we give a little room motor the current to be more imbalanced than the voltage, right? So, okay, so now this is what happened here. So this is what happened. So I will be doing this, right? So I will do 110 volt at angle of 0 degrees, right? And I am dividing this by this. So I'm dividing by 16.155 at angle of 21.8 degrees. Okay, so when I do this math, it's straightforward, right? So that's straightforward. And I get divided by 16.155 is equal to 6.8. Is equal to 6.8, right? Now, when I have the angles, I bring this out and I subtract it from this, right? If I subtract it from that, that means that I will have a negative, this current will be a negative 21.8 degrees. And that is amps, right? Okay, so I got the first one. Now let's do the second one. Well, the only one, the value is going to be the same. The only one is going to change is this, right? Now, so let's do it. So in this case, I will do IV is equal to 110, right? I call that IV, right? Because it's in the, no, actually IC, this is IC. Okay, never mind. This is IV. IV is this, it's 120 at negative 120 degrees, right? And I am dividing that by the same, so it's going to be 16.155 angle of 21.8 degrees. Now, when I do that, that is going to be, it's going to be the same number, so it's going to be 6.8, but the angle is going to change, right? Because I am subtracting this, and then that is negative already, and then I am subtracting that, so that will become 141.8. 141.8. So that is 100 negative 141.8 degrees. All right. Okay. So, okay. Right. So now let's do the next. Let's do IC. IC, right, is equal to 240. I'm sorry, it's equal to 110 at angle negative 240 degrees. Now, doing the same thing, right? So 16.155, and that is going to be equal to, now I am adding 21, right? 21.8, so it's going to be 6.8. It's going to be right here, 21.8 degrees. So subtracting that from the top, and this is already negative, it's going to be minus times minus and a minus, which is going to be adding the two numbers, which is going to be 261.8 to negative 61.8 degrees. All right, now, okay, so I am going to explain this 240 because somebody can say, oh, they add a phase because this vector is a 0, right? Like, if I do right, if I actually so right, so right here somebody can say, well, this makes sense because it's a 0, right? This is a 0, right? And then this will also make sense because of 120, negative 120, which this vector is laying right here, right? Okay, so that makes sense, right? 0 degrees, but then I go 120 degrees, approximately 120 degrees right here. Oh, that makes sense too, right? Because it's a negative 120 degrees, right? Negative 120 degrees. Okay, but they sometimes say, oh, this are not in phase because this is 240. Well, by definition, we say that V, whatever VP, V phase at 240 degrees, is the same as VP at plus 120 degrees. Okay. So, okay. They say, okay, so how can we prove this, right? Well, if you take, remember, if I go like this, I am going, actually this is positive, sorry. Technically it's supposed to be positive. Yeah, but anyway, it's the same thing. So let's say that it went, right? So, and a positive, right? I go like this. Positive to 180, right? Okay, like this. This is positive, but if I went like this, there's a negative. So this vector, this right here is technically somewhere over here, right? This is negative 120. Right. But then I go again and I go in the same direction. I go in the same direction and I go like this. So I go, I get to 120. Go up. I get to what? I get to 240, right? Now, you don't believe me. You don't believe me, take your calculator and make sure it's in degree mode, right? Well, you can do it in radians too, as long as, you know. And put the cosine of 120, negative 120, and then the cosine, actually the cosine of 120, right? The cosine of 120 degrees is negative 0.5, right? Negative 0.5. And also, the cosine of negative 240 is also negative 1.5. Why? Because I am still still in the same quadrant. You can see that this is the hypotenuse of this. This is the hypotenuse, right? And this is the sine, this right here. This is the sine, right? And this is the hypotenuse. And this right here is the cosine, so I am a negative. I am in the negative axis and the cosine, so therefore that's why the value is negative 0.5 on both. So because right here I go, and this is equal to negative 240 degrees. See? I go like this, I get the same value, and then I go like this, I get the same value. See? That's how we get that by definition that VP at 240 degrees is the same as VP at plus 120 degrees, right? So with that being said, that's why I want to get that, because this, so this right here is cosine theta. This right here is sine theta, right? So yeah, so basically, and there's a little angle right there that that represents that. This is the hypotenuse. Oh, this is the angle. This is hypotenuse, right? So technically, that vector and going in that direction, the hypotenuse is the same if you're going from 0 to positive, from 0 to positive 120, or from 0 to negative 240 degrees. It's the same value. So I hope this video helps anybody who is taking circuits, right? But we proved that if you have a balanced system, you will have the same current, right? If you have a balanced system, you would have the same current. And how we know we have the balanced system is by making sure that we actually see the values of the impedance are the same. If the impedance and the loss size are the same value in every single phase, again, if the impedance in the load are the same values in every single phase, then, or line, right? Line, I will say line because it's line, right? Then that will equalize the system, and then we will have a balanced system. If we don't have if these are not the same, if the impedance are not the same, then we have an imbalanced system, right? So if you hook up in this phase, 15 motors, and you hook up maybe 5 motors over here, and with the same value of impedances, and well, 15 is going to be, it's going to be bigger than 5 motors, right? And then you hook up 10 motors over here. So guess what? IA is going to carry more load. IB is going to carry, less load. And then IC is going to carry more load, but it's going to be, this will carry less load than this one, both of this. So therefore, it will be unbalanced. It will be unbalanced, right? But in this case, so if you have the same amount, the same amount of impedance on every single line that pertains to each phase, right? And then let me make this clear again. If you have the same amount of impedance in each line that pertains to each phase of the system, right? Then you have a balanced load. In this case, this is a Y-to-Y system. Thank you for watching, and I see you in the next video. Remember that we learn every little bit of everything over here in this channel related to engineering, because Jesus is good. Thank you for watching.